Okay. Thank you, Yanis. Thank you, the organizers. It's a great pleasure for me to be here, even though we're not in Crete, in this virtual format. And I would like to present some recent results that we have been having with several graduate students and postdocs that are listed here, and for whom I'm really grateful, regarding sweeps and flares from magnetic reconnection in blazar jets. So I owe you a definition of what reconnection is. In words by Russell Cosroot at his 90th birthday party, Enrico Fermi told me to study reconnection for my PhD thesis 70 years ago, and here we are, and we still don't understand it. Given this, let me just say reconnection is a process by which magnetic field energy can be transferred to the particles, sometimes very efficiently. And this is done by essentially breaking the magnetic field lines. The breaking of the magnetic field lines allows to transfer the magnetic energy into particles. Blazar jets and other astrophysical systems are giving us a unique opportunity, which is to study reconnection in a very strongly magnetized regime. And what do I mean by that? If you take this parameter, sigma, magnetization, that is defined as the ratio of the magnetic energy density to the plasma rest mass energy density, the astrophysical systems, including blazar jets, have the capability of studying or giving us a probe of magnetic reconnection in the sigma much larger than unity regime, which is impossible in the lab or near the Earth magnetosphere. This parameter will come back over and over again during my talk. Again, ratio of magnetic energy density to the plasma rest mass energy density. How can we study reconnection? Most of what I'm going to present in my presentation today is done with particle in cell simulations. Particle in cell simulations allow to capture the interplay of charged particles and electromagnetic fields from a very fundamental level. You basically solve the particle motion under the Lorentz force, and the particles are then used, and their electric currents are then used to solve for the electric and the magnetic fields in Maxwell's equations. Nothing more fundamental than that. You cannot go more fundamental than that. The pro is that we can capture the physics of particle acceleration from a fundamental level. The con, the disadvantage, is the fact that the time scales of plasmas and the length scales of plasmas are much smaller than astrophysical scales. So they're listed here. The 0 megap is called plasma skin depth. It is the inverse of the plasma frequency, the characteristic plasma time. They're much smaller than astronomical timescale. So careful extrapolation is needed from plasma scales to astronomical scales. How does reconnection look like in a particle in cell simulation? This is a three-dimensional particle in cell simulation with a magnetization of 10, so 10 times more energy initially in the magnetic field than in the particle rest mass, which means that if you are able to dissipate the magnetic field energy, the particles will immediately become ultra-relativistic because the magnetic energy is much larger than the rest mass energy of the plasma. We start with an anti-parallel magnetic field, as shown here by the arrows, and the system evolves in a very dynamic way. It creates these structures, which we call magnetic islands or plasmoids, which merge, constantly are created over time, move left and right, sometimes with relativistic motions. I will come back to some of these aspects later on. So now I gave you a sort of like a crash course, 3-minute crash course on what magnetic reconnection is. Now let's put this in the context of blazars or relativistic jets in general. As we all know, blazars are jets from AGNs that are pointing along our line of sight. So I'm taking here the image from MET7, which is actually not a blazar, but imagine to put your telescope into the jet, to look into the jet. And magnetic reconnection can happen in such jets due to a variety of global properties, global evolution. In one case, you can imagine having the magnetic field threading the accretion flow, switching polarity, up, earlier time, down, later time, larger radii. So the initial magnetic field that is accreted into the black hole will be giving rise to a jet in which the toroidal field is going around in one direction. Later on, opposite polarity accreted to the black hole, the field in the jet is toroidal, going out in the opposite direction. So at the interface between the two, you have this anti-parallel magnetic field, which we have just discussed, being the basis for magnetic reconnection. There have been also global MHD simulations showing that reconnection does happen in relativistic jets, in blazar jets. This is due to a different process. It's an MHD instability, which is called Kink instability of a toroidal magnetic field, which gets rearranged, and its nonlinear stages are leading to dissipation of the magnetic energy due to reconnection. Now we have a global picture of where reconnection and why reconnection may be happening in blazar jets. And now let's understand a little bit more the prospects of reconnection in producing high energy particles and resulting emission. So first thing, reconnection needs to be able to explain highly non-thermal particle spectra. And by that, I mean the requirement that is often, I would say always inferred from the observations of a emitting electron population such that the number of particles over its Lorentz factor or energy scales like energy or Lorentz factor to the minus p for some power law slope p, which sometimes is harder than 2. This is a typical blazar spectrum. Reconnection can naturally give such population. The results here are for an electron-positron plasma, but now the same conclusion has been tested for electron-proton, electron-positron proton plasma. So reconnection quite generically is able to produce non-thermal particles, power laws that have a hard slope less than 2 for high magnetizations. And again, let me remind you, magnetization is the ratio of the magnetic energy to the rest mass energy of the plasma. So a variety of power law slopes, hard slopes for high magnetizations. The second property of reconnection in the context of blazar emission that I would like to focus on is the main topic, one of the main topics of this workshop, optical polarization rotations. This is work done by David Hosking. And by that, I mean, as we all know, enhancement in the optical flux or generally flares that are associated in conjunction with large angle polarization angle rotation, PA rotations in short, on a day or so time period. This is one of the examples. You will see many more from the speakers in the remainder of this session. And let me also emphasize how Cheng will also be talking about polarization in reconnection later on this morning or afternoon, depending on where you are. So please listen to his talk as well. So to understand a little bit more about polarization angle rotations, let's step back 1 second. Let's look at the dynamics of the reconnection layer a little bit more from PIC simulations. Again, starting with this anti-parallel magnetic field, let's let it evolve. This is very dynamic. It produces these plasmoids or magnetic islands. I would like to emphasize here 2 main properties that are instrumental for what I will be discussing later. You'll have large plasmoids that are accreting a number of smaller plasmoids from the backside. That's very generic. You just saw it, you're seeing it again. Large plasmoids are moving slower than smaller plasmoids, and they're gonna be hit back from their backside by smaller plasmoids accreting into them. Smaller trailing plasmoids accreting into larger leading plasmoids. The second property is that the largest plasmoids, quite generically, have a size that is 10% of the size of the system. It's another generic conclusion, regardless of the system size. So before moving into the details of our model for polarization angle rotations, let me just give you a cartoonish picture of it. This is our reconnection layer. And I'm gonna focus on one plasmoid now. This is the magnetic field lines around that plasmoid. In this simulation, we're also adding a little bit of a component of the magnetic field that is sticking out of the page, so pointing towards me. We call this guide field. And now imagine that you're just getting the emission from this plasmoid, and in particular, only from an emission front that somehow, I will say this later why, sweeps through the plasmoid. So this is in orange, the emission front, and the white are the magnetic field lines of the plasmoid in the plane of the presentation or the board. So at this time T1, the plane of sky magnetic field is pointing up. So let's put this data point here. At later time, the emission front has swept past the side of the plasmoid and it's sitting in the middle of the plasmoid. Now, there is no plane of sky projection of the magnetic field that I'm depicting here, but there is still this guide field that is pointing at me. So this is giving us the polarization angle now at 90 degrees. And later on, emission front is on the other side of the plasmoid. The situation is reversed as compared to time t1, and the polarization angle is opposite with respect to time t1. So bottom line, if you have an emission front that is sweeping through the plasmoid, the projection of the magnetic field on the plane of the sky and so the polarization angle are expected to rotate by some amount, in the extreme case, 180 degrees. So now we're back to the source of that emission front. So for that, we need to do particle in cell simulations, and we need to do particle in cell simulations with synchrotron cooling or inverse Compton cooling. The conclusions don't change depending on the source of cooling. We have done the case of synchrotron cooling. We parameterize the strength of the cooling losses with a characteristic Lorentz factor that I'm calling gamma critical, that is defined by taking the accelerating power of the electric field induced by reconnection and equating it to the synchrotron cooling loss power. This is the definition of gamma critical. Very large gamma critical means very little cooling. Very low gamma critical means very strong cooling. I'm listing here the parameters expected for blazar jets and the parameters in our simulations. Numbers are different, but the hierarchy of the Lorentz factors is the same. In particular, the characteristic Lorentz factor at which particles are accelerated, which is of order sigma, sigma is a statement of the mean energy per particle, is smaller than this critical Lorentz factor, as it should be. Same thing in blazar jets. And also, as in blazar jets, the cooling Lorentz factor, meaning such that the particles are cooling on a dynamical time, is of order 0.1 of the characteristic Lorentz factor gamma sigma, which, as I said, is of order sigma, the magnetization. Same thing for blazar jets. So we're getting the right hierarchy of energy scales. The important point that I would like to emphasize is just the one that I mentioned. The cooling time at gamma sigma is of order of 10% of the dynamical time. But since the size of the largest plasmoids, as I said earlier, is of order 0.1 of the size of the system, then the cooling time for a particle streaming through the large plasmoid is of order of the same as the crossing time of that same particle. So particles cool while sweeping, while crossing the plasmoid along the magnetic field. And this is illustrated by this movie, which comes from our particle in cell simulation. I'm gonna describe what you will see in the movie. In the top panel right here, it's a 2D plot in the YX plane of the simulation of the synchron emissivity. And the bottom panel right here is the projection, it's the integration of the synchron emissivity along the Y direction. The cyan is the local polarization angle. So you will see from the bottom panel, especially, that emission front sweeping through regions with opposite polarization angle, which is the reason for why you get the sweep, the polarization angle sweep. The emission front starts now as this plasmoid merges into the bigger one. This generates high energy particles. The high energy particles are causing this emission front to sweep through the plasmoid. I will let it run again. The merger is happening now, and you're seeing this emission front sweeping through, illuminating regions with different magnetic field orientation or polarization angle, and so causing the polarization angle sweep. So we do get the flares from particles accelerated at the merger interface. We do get the sweep because the emission front sweeps through regions with different plane of sky magnetic field. I have a few more words on this. The peak frequency falls naturally in the optical band. We are relying on this matching of timescales between the optical cooling time, the cooling time of optically emitting particles, and the time for the particles to sweep through the plasmoid, to circle the plasmoid. This also implies that higher frequencies, the cooling time would be much smaller than the light crossing time. So based on this model, I would not expect significant polarization angle sweeps in the X-rays. Let me skip this one. Rotations of 180 degrees are naturally expected if you have a weak guide field, out of plane magnetic field. How do you get even more than 180 degrees? I would claim that this can only be due to multiple mergers. So multiple of these projectiles, plasmoids passing through and generating sweeps through a larger plasmoid. This naturally happens, but this would also say that in reality, very large angle rotations should be associated with a number of flares if we're associating every flare with a merger. In the last 3 minutes, I would like to present one more implication of reconnection in the context of blazars. And this is related to the so-called orphan gamma ray flares, appearing in the gamma rays, but not in the optical. They don't have optical counterpart. And here, I would like to embed reconnection in a little bit more of a global picture. Turbulence, we have discovered in recent years, naturally leads to magnetic reconnection. This is a sweep through various boxes in our simulation showing that you have, for example, these plasmoids, I just froze it now, resulting from reconnection within a globally turbulent scenario. This is consistent with earlier results on the same topic. The important thing for us is that the process of acceleration of particles here happens in 2 stages. This is one particle. You see the particle here. You will see the same particle here in the zoom in. The particle is getting its first kick in energy now. You see the particle Lorentz factor just increased. This is happening while the particle is sitting in a reconnection layer. So the first energization of particles in turbulence, magnetically dominated turbulence, is due to reconnection. And then you can continue by having the particles scattering back and forth as in our usual picture of particle acceleration in turbulence. But the first acceleration event is the reconnection, is due to reconnection. And this is quite generic. It's true for all particles. Initially, you are accelerated to a Lorentz factor of order sigma, quite abruptly on very short time scales. And later on, acceleration by scattering of turbulent fluctuation picks up, but it's happening on a slower time scale. So what is the consequence of this for orphan gamma ray flares? So let's again do our simulations with cooling. This time it needs to be inverse Compton cooling because the orphan flares are radiating
3 more minutes,
rays.
Lorenzo.
Got it. And not much in the synchrotron. Again, the hierarchy is preserved in our simulations as compared to blazar jets. The important point is if you're adding cooling, the initial episode of energization due to reconnection is unaffected because it's happening on very fast time scales. But a subsequent acceleration by scattering of turbulent fluctuations does not happen because the particles cool well before experiencing the second acceleration scenario. So reconnection is the only agent of acceleration active in a turbulent environment when particles are in the fast cooling regime. This has 2 consequences. First, the particles don't move very far from the reconnection layers where they got accelerated in the first place. Here you see the particle energy is associated, is tracking basically the structure of currents in our turbulence simulations. But most importantly, this has very important consequences for the pitch angle of the particle, the direction between the angle between the particle velocity and the magnetic field. In particular, particles energized by reconnection tend to be moving along the magnetic field, almost along the magnetic field. Whereas particles accelerated by turbulence tend to move perpendicular to the magnetic field. But in strong cooling, the second scenario is not allowed. So the only energized particles in fast cooling blazar scenarios have to be moving quite parallel to the magnetic field, small pitch angles. And now we all know the synchrotron emission scales like sine squared of the pitch angle. So for very small pitch angles, synchrotron emission is very suppressed, is very much suppressed. And in fact, in this case, we have derived a light curve from our simulations in which we pick initially the same ratio of the same value for the magnetic energy density and the radiation energy density. And yet the synchron luminosity is comparable to the inverse Compton luminosity only when we scale it up by a factor of 1,000. And that's exactly because of this sine squared alpha effect. So pitch angle is critical to understand orphan gamma ray flares. And I will leave this. Here my conclusions. Thank you.
Thank you very much, Lorenzo. We have time for one quick question. If you can just raise your hand. Timur, please go ahead.
Hello. So I have just a quick question to ask, and thank you for the presentation. I'm a spectroscopy guy, but not actually professional in such simulations. But I would like to ask that, how do you define reconnection regions in those simulations? Thank you.
Yeah, so it's an excellent question. So I would say reconnection is happening whenever you have dissipation of the magnetic field induced as a result of alternating fields. And this is happening quite generically, but it ultimately comes down to what is the geometry of magnetic fields in jets, which I think is a very important open question as well. I'm trying to understand it from the point of view of what are the consequences for the emission. But the other side of things is, for example, global polarization of jets versus global MHD simulations of jet launching that are able to let us know a little bit more about the structure of the magnetic fields in jets.
Thank you very much, Lorenzo. Excellent presentation.